All right, let's get into chapter 14 of the Powell text, Monte Carlo simulation. All right, so what is a Monte Carlo simulation? Okay, it is a way of performing calculations or providing estimates, modeling different situations under uncertainty. Okay, a little bit like the last chapter with decision trees, but a bit more sophisticated. Okay. Monte Carlo simulation, or simulation as we call it, can tell us not only what the outcomes of a decision could be, but the probability of those outcomes. And in fact, the result of the simulation is a probability distribution of the outcomes. Okay, so you don't just get a outcome, but you get the probability of that outcome occurring. Okay, and so in a way, this is a sophisticated and advanced form of sensitivity analysis. All right, so why do it? What happens is we sometimes want to determine the probability of an outcome. Okay, the outcomes are not deterministic. All right, they are based on a set of improbable inputs. Okay, not improbable, but uncertain inputs. Okay, and so when we have uncertainty, there is a measure of risk. Okay. And so if something is 90% probable, that's a lot less risky than if something is 60% probable. Okay. And so this is important to us. All right. And so decision trees allow us to make decisions under some uncertainty and some risk. Okay. When we're dealing with a large number of uncertainties or complex models, then Monte Carlo simulation is a better method. Okay. But we do have to remember that the results are a probability distribution for the outcome, not a single value for the outcome. These are not deterministic. All right, and so then it is left up to the decision maker to look at the results of the simulation and see what insights they can gain from it. So let's talk about the steps in doing a simulation. Okay, the first thing we do is we start with a base case. All right, and which of our input parameters are uncertain. Okay, and so this is really no different than what we've been doing all semester. Okay, we model the base case. All right, before we run any optimization or anything like that, we put the model together. All right, we might put in some dummy variables for the inputs, and then we have to figure out which of our inputs are uncertain. Okay, and then we also have to decide what type of probability distribution is going to be for those inputs, and we'll take a look at that a little closer in a few slides. All right, and then we take random samples for the inputs and calculate the output. So basically, we put a random number into the inputs and we see how the output changes. Okay. Now, Monte Carlo simulation does this automatically, but we could do this by hand if we want to. But who wants to do this 1,000 or 5,000 times? Okay. And then finally, we can create a graph, a histogram of the outcomes, and then interpret it. All right. And we're going to see a probability distribution of the outcome, and most of the time we're looking for the mean or the average of those outcomes. And so the Monte Carlo simulator will give us mean values, also called expected values, and also, if we want it, something called tail probabilities. All right. So, for example, we'll see this in one of our examples coming up: the probability of a positive profit. Okay. All right. So A lot of times people don't know where to begin with Monte Carlo simulation, but as I said, build the model as if you had no uncertainty, okay? As if all of your parameters, all of your inputs are known, okay? And then, so you build the model, you put things in their place, you make it very readable, very interpretable. You make sure your calculations are correct, all right? And then you move on, okay? So you fix what we know will be random at some arbitrary value, okay? And then we check our calculations, debug the spreadsheet as if there was no uncertainty, all right? And then only after that do we introduce uncertainty. All right. Fluctuation in sales, fluctuation in demand or costs, or whatever it is that we deem to be uncertain. So, the summary of the simulation process: we figure out what parameters are uncertain. We decide what kind of a probability distribution they will take. Okay. And you can, if you're a mathematician, you can decide this yourself, or you might get this from your data analysis people. Okay. But you need to decide what kind of a probability distribution that the parameters will be subject to. We select the outputs. Okay, what is it that we are trying to ultimately decide? Okay, what is our output? Is it cost? Is it sales? Is it revenue? And so on. So then we run the simulation and we analyze our output. Okay, so how do we select a probability distribution? Okay, is it discrete? I mean, does it take the form of integers, for example? Is it uniform, normal, triangular, or something else? Okay. Now, all of you have probably had statistics or some type of training in probability. If not, go back, and these are fairly simple concepts, but you need to go back and make sure you know what we mean by mean and standard deviation, a normal curve, that kind of thing. All right. And although our simulator, analytic solver platform, and others have lots of different distributions, really we're only going to choose from a small handful of them. We have two different types of data. Okay, they are empirical data and judgmental data. Okay, empirical data is what you have actually observed. Okay, so historical data from sales, for example, is empirical data. Judgmental data are estimates or forecasts. Okay, so empirical data kind of looks to the past. Judgmental data is what's likely to occur in the future. All right. And so decision makers, or those helping us make the decision and model it, will often be able to provide you with probability estimates such as the mean, the min or the max, or the 10th or 90th percentiles if you're thinking of a normal curve. All right, so a lot of times empirical data is not sufficient. Okay, in a lot of cases, there might be no empirical data. All right, however, forecasts are often available, and that falls under judgmental data. Now, granted, judgmental data is usually more accurate when it is based on empirical data. But for example, if you're starting a new business, then you don't have any empirical data. You don't have any historical sales, that kind of thing. Even if you have empirical data available to you, it might be biased or it might not work for what you are trying to figure out. Okay? So we have to take that empirical data and still make judgments about it. Okay? So we still have to fit a probability distribution, for example, to that data so that when we model it, when we simulate it, we know which distribution to use. Okay? For the most part, what we are interested in is the mean and the variance, or the mean and the standard deviation of an uncertain parameter. And then if it takes the form of a binomial distribution or a normal distribution, it's not as big a deal to us. As long as we know the mean and the variance, those are the most important things. So there are six standard distributions or essential distributions that we will usually choose from. All right. As I said, there are lots of others, but typically uh, the ones that we will most often use fall within these six. And the first is the Bernoulli distribution. Okay. And this is where the uncertain parameter can really only take two possible values. So, for example, if we were modeling a coin flip, all right, it's either heads or tails. Okay, heads or tails would be a Bernoulli distribution. A yes/no situation would be a Bernoulli distribution. Okay, the integer uniform distribution is when we model a random outcome that takes on a small number of discrete values, and those values have got to be equally probable. The most common or the easiest way to think of this as the toss of a dice, a toss of a die. All right, it can come up with uh, 1, 2, 3, 4, 5, or 6, and each of those outcomes is equally probable. All right, assuming the die isn't fixed in some way. Okay, so it's a small number, 6, discrete values, it's not continuous, okay, and they are equally probable. The binomial distribution kind of looks in many ways like a normal distribution. But it is for discrete values. If you were sampling people as to their whether they voted Democrat or Republican, for example, that would be a binomial distribution. All right. Uniform distribution is an outcome that's equally likely to fall anywhere between the minimum and the maximum. All right. And so it's like the integer uniform distribution, but the values don't have to be integers. The triangular distribution is something we're going to show you in an example here. It's very flexible, and you define it by three parameters: the minimum value, the maximum value, and the most likely value. Okay, and you'll see that in a few slides. And then lastly, the one that we're probably most familiar with is the normal distribution, and it's what we call the bell curve, right? It's usually symmetrical, and we specify it by its mean and the standard deviation. Standard deviation is a measure of the variability of the normal curve. Okay. So this is a graphic of the Bernoulli distribution. Only two possible outcomes. Okay. Now notice those two possible outcomes do not have to be equally probable. All right. So as you can see, the outcome on the right is far more probable than the outcome on the left. So this is obviously not a coin flip unless you've fixed the coin. Okay. But this is what a Bernoulli distribution looks like. An integer uniform distribution, as we say, is has a discrete number of outcomes. In this case, it's 10, and they are all equally probable. All right. If this was a 10-sided die, this is what it would look like. Binomial distribution, as I said, it's discrete. It uses discrete values, but it looks pretty much like a normal curve. If you were to ask people, as I said, whether they voted or favored Republicans or Democrats, all right, you'd get a distribution that looks something like this. Uniform distribution is continuous. Well, that's why there are no gaps in the graph. But again, all values are equally likely between the minimum and the maximum. Here we have the triangular distribution. Notice that it is not a symmetrical triangle. It can be, but in this case, it is not. Because if you look over here on the right, we have the three parameters, which are minimum, maximum, and the likely value. The likely value of 125 is closer to the maximum of 150 than it is from the minimum of 50. So it looks like it's leaning to the right because it is. And then finally, we have the normal distribution. And if you remember anything about statistics or probability, you should remember this. Okay, a lot of probable or uncertain outcomes take the form of what we call the normal distribution. All right. And over on the right, we have the parameters that we will typically supply for a normal distribution, and that is the mean and the standard deviation. And as I said, the standard deviation is the a measure of the variance of the data. Okay, so a larger standard deviation will create a fatter curve. All right, whereas a lower standard deviation will produce a narrower curve where things are closer to the mean. So let's take a look at an example that is in the book. All right. And this example is also on the chapter spreadsheet. Now, one thing, I have condensed this lecture. The book chapter is actually a lot bigger than the lecture would indicate. All right. I'm not going to give all of the examples that are outlined in the book. It seemed to me that it was a case of kind of beating a dead horse after a while. So I'm going to give you a couple of examples. You can absolutely work through what's in the book, okay? But I didn't think it was necessary to go over every single one in the lecture, all right? And so I'll just give you a few, and then we'll sum it up, and you'll get the idea. Now, so we have advertising budget model. This is actually an optimization model, okay, as you can see from the form it takes, but we're not going to deal with optimization right now, okay? So our ad expenditures, for example, we've just fixed in this case to 10,000 each. And up at the top, you can see that what we're trying to do is maximize our profit, and we maximize profit by selling a certain number of units. And this is the formula that we use to determine the units sold, and it is a function of different sales parameters and the ad expenditures. Okay, and as you might guess, what you're willing to spend on ads has an impact on the number of units that you would sell. Okay, so this is the base case. We haven't done anything uncertain here. This is a deterministic model. Okay, the price is fixed at 40. The cost is fixed at 25. We have our equation. So all we end up deciding is how much of our $40,000 ad budget to distribute in the different quarters. Okay, we arbitrarily fix them at 10,000. All right, so nothing is uncertain here. This is our base case. Okay, so but what suppose price and cost are actually not fixed. All right, suppose they are, they do have some uncertainty. Okay, so what we can do is, you notice it here at the top, is we can set Analytic Solver platform to provide a random input for price from a triangular distribution. All right, and also a random input for cost from a triangular distribution. So again, triangular distribution provides a minimum and a maximum and the most likely value. Okay, and then what we do is we specify in the solver platform that this is the outcome here, which is profit. Okay, and right now it's based on random values. All right, it is a function of price and cost. Okay, so when we run the simulation, and the book shows you how to run simulations, and I'll show you when we do our synchronous session. Okay, but when you run the simulation, you get a histogram of results that look like this. Okay, that notice that although the inputs were a triangular distribution, the output is not necessarily. Okay, so we come up with a mean value of 147,000. Okay, and so that is going to be based on I think it's like 1,000 trial runs. All right, we get a mean profit of 147,000. Now it has quite a large standard deviation here, okay, of 99,000. All right, and so that's why this curve looks somewhat fat. All right, because it has a large standard deviation. Okay, and notice we also have calculated the tail probability. All right, and that is that there is a 92% chance of being greater than zero. So there's a 92% chance of a positive profit. Now that's pretty good. All right. All right. Second example, Butson Stores. All right. And this is the base case, and this is articulated. I'm not going to go through all of the calculations here. This is articulated in the book, okay? But essentially, we have monthly sales, all right? The December sales are known, but the January through June sales are estimates, all right? And so our forecasting folks have given us the mean and the standard deviation. All right. And in this particular case, in the base case, we're not using the standard deviation at all. All right. And so we are able to calculate our revenue, our costs, how much in order to keep a minimum of $250,000 worth of cash on hand. We sometimes have to borrow money and pay interest on that. Okay. And so, what we want to find out ultimately is the amount of our maximum loan. Okay. And in this case, it turns out to be in April, and the cumulative interest that we're going to have to pay, which is $12,000. Okay. And so this is our base case. Nothing here is uncertain. All right. We have not built in any uncertainty. What we've done for the sales is just transferred the mean values from up here to down here. Okay. So base case, always start with your base case with no uncertainty, just to check your calculations and make sure everything is working properly. Let's talk about sensitivity analysis for a moment. All right, and that's nothing new. We've already done sensitivity analysis, but Analytics Solver platform allows us to do sensitivity analysis in kind of a cool way. If we select the cell, one of our output cells, and we go to parameters identify, we get these results, and these are called tornado charts for obvious reasons. You can see that they're shaped like a tornado, and what it does, it allows us to see the parameters in descending order, if you will, that most influence our outcome. Okay, so as you can see for both C32, which is our maximum loan, and C33, which is our interest paid, the most the outcomes are most sensitive to C9, which is our material cost percentage. All right, and then it goes down from there. All right, so this is kind of cool. It allows us to see very quickly which parameters our outcomes are most sensitive to. All right, and that's the whole point of sensitivity analysis. So we run sensitivity analysis before we do a simulation. We would run it on our base case. All right, give us a little bit of insight into what is going on here. All right, and then we can run our simulation. And so what we have done in this case is for the January to June values, we have added the uncertainty parameters, and essentially we have told put in the spreadsheet that these are going to be normal curves, normal distribution, and we have entered the standard deviation and the mean. Okay, and so these values are random within those parameters. So January is the mean is 1800, the standard deviation is 80, as you can see up here. And when you put that in there, you get a random input of, in this case, 1784.9. Okay, and then at the bottom we have our simulation output cells. All right, and again, I will show you how to do this when we do our synchronous session, but you really ought to play with this yourself before we get into our session so that it's not completely new to you. Okay? And these are the results. We get a histogram on the left-hand side. This is our maximum loan. And on the right-hand side is our interest. Okay. And as you can see, we have a mean of 648 and for the maximum loan and a mean of 12.37 for our interest paid. Those are actually very close to our base case models. So in this case, introducing uncertainty did not change our results very much. All right. But that's a good thing. Okay. It means we have a robust model that holds up to uncertainty. All right. And that's a result in itself. Now, in a lot of cases, what we do is we double click on the result to get the histograms like we saw in the last case, all right, or in the last slide. But we can also, and so what ends up, the value that ends up being in the outputs is random. It is not necessarily our mean, okay? But we can display the mean in a different cell and a number of other parameters, okay? And this is important because if we run the simulation lots of different times, we can record the results directly on the spreadsheet. All right. And as I said, ASP provides this value, the mean value, and other statistical values that we would use. Typically, what we're going to do is display the mean, maybe the standard error. Okay. And so I will show you how to use the sci-mean function when we do our synchronous session. And it is used on the Butson spreadsheet in the chapter spreadsheets. So when do we simulate and when do we not bother simulating? Okay. It says occasionally we may go to the trouble of conducting a simulation only to discover that the effort could have been avoided. Frankly, in the last case, our simulation yielded very much the same results as our base case model. All right. But honestly, in many cases, you don't know until you run the simulation that you didn't have to. Okay. So we don't know in advance whether we're going to do this or not. And, and so unless we have an idea that, for example, our model is linear, then simulation is a good general purpose tool for using in uncertain with uncertain parameters, uncertain situations. Okay. So as I mentioned, I didn't go through all of the examples that are in the book. Okay, that just seemed a little bit like overkill. Okay, go through them, take a look at them, but it all boils down to pretty much the same thing. You build a base case like we've been doing all semester. All right, but instead of optimization, instead of identifying decision variables, we are identifying uncertain variables, uncertain parameters. And then we identify them and label them as uncertain. We give them a probability distribution, okay, that most matches what the data is likely to look like. We identify outputs in the spreadsheet of the simulation, and then we run the simulation, okay. But before we do that, when we have our base case, we run a sensitivity analysis, and we can do things like the data table in Excel, which we've done, or now we can use tornado charts, which are really kind of a neat way of seeing which input parameters have the biggest impact on the outcome. All right, and then if we not want to, we can focus on those big impact items as the focus of uncertainty. All right, every simulation involves four major activities. Identify the uncertain parameters, select the probability distribution, Ensure precision in the outcomes, and that usually means running the simulation enough times to come up with something valid. Typically, the greater number of observations you have, the more precise your outcomes are. Okay, and then you interpret the outcome distribution. All right. Its simulation is more sophisticated than the simple modeling we've been done, but it is very powerful. Okay, but as with optimization, one of the big challenges is translating the results into a form that managers can understand. All right, and make a decision. This is about making decisions. The whole point of this class is about enabling decisions. All right, the interpretation is sometimes subjective. All right. It depends on what the decision makers value. It depends on the imperatives that the decision makers are subject to within their organization. All right. Sometimes it's maximizing profit. Sometimes it's minimizing cost. But sometimes it can be more complex than that. Okay. So we're not here to tell you which is the right interpretation of a spreadsheet model, whether it's optimization or simulation. It's just to provide you with the tools that you need to do the interpretation. Okay, that's it for this chapter, and I will see you guys in the synchronous session.